In this lecture, we are going to learn about what we call the exact equation. So, exact equations. Exact equations. So, what we're trying to do, we're going to learn something called the differential of a function of two variables. So, differential of a function, differential of a function of two variables. So what's the differential of a function of two variables? You already know a differential of a function of one variable, so it will be clear in a minute. So let's write about that. So what is that? So if z equal fxy, so z is the variable. If z equal fxy is a function of x and y with we're gonna say continuous with continuous, so we say series continuous first partial derivatives with continuous first partial derivatives, continuous first partial derivatives with continuous first partial derivatives in a region R. So we're going to say R in region R. So let's say you have a region, you're going to call that region R. So in this region, this function has continuous first partial derivatives. So in this case, then its derivatives, then it's we're going to say then it's a differential, its differential is defined as the differential is defined as we're going to say it is dz equal da bar f over da bar x dx. So there are two derivatives here, okay, because these are partial derivatives. The first one is partial derivatives, and the partial derivative of f with respect to y dy. So there are partial and the regular derivatives. So this is what we call the differential of the z function. Okay? Differential of the z function. So what are the important things? So you define a function z which is a function of two variables x and y. If this is the case, then we define what we call the differential of the function by this. So this is what we call the differential of the function f. Okay, that's the differential, called the differential of the function. So actually, what is the differential? So this differential is if you make a change in the x direction and the y direction, what is the change that's going to happen in the z direction? So there are two variables here, x and y. So that means if you try to plot them here, so these are the two variables. There's an x variable and also there's a y variable. So the thing is that what will happen to the z function if you make slight changes in the x direction and y direction? What will happen to the z function? So it's given by this. This is what we call the differential of the z function. So the differential of z equal da by f over da by y times dx plus da by f over da by y dy. So so these are partial derivatives. So these two are partial derivatives. It's not d, it's da, but it's a partial derivative. So these are partial derivatives. Partial derivatives. Good. And then we also talk about partial derivatives in a previous lecture and how to find them. So this is about So if you go to the characterization, the classification of differential equations, in the classification video we talk about partial derivatives, and we also found few of them. Now let's see what's going to happen in a special situation. Now, so let's say if the function fxy is a constant, so let's say this is a constant function, so it's a special case, very special case, then what's going to happen, so then what's going to happen, the function, the differential is the change in the z function is 0, so right, so the differential going to be 0 in this case. So if this is the case, then what's going to happen, da by f over da by x times dx plus da by f over da by y dy, because there is no change in the z function because it's a constant function, so that means has to be 0. So that is the key part for what we're trying to do today. So that means if the function is a constant function, it's not going to happen always. If the function is a constant function, there cannot be change in the function even if we change x and y. So in that case, what will happen, the differential is simply equal to 0. Okay, differential is simply equal to 0. So so I'm going to call this actually equation number 2, and the differential I'm going to call equation number 1. So let's call this equation number 1. So this is equation number 1. So equation number 2 is the differential. Equation number 1 is the differential. Equation number 2 is what happen if the function is a constant. So it's a consequence. It's not always. It's a consequence of this. So that means if the function is a constant function, what's going to happen? If the function is a constant function, what's going to happen? The differential going to be equal to 0. Okay. Now the goal is we try to go backward. So the goal is, if you know equation number 2, can we find the function? That means, can we find that constant function? So that's the goal. Okay, so let's talk about that. So the goal is, we can say if we know 2, equation number 2, that means the differential equal to 0. So the question is, can we find a function, a constant function fxy equal to c? Can we do that? Okay, so that's the goal. If you know equation number 2, so let's go back. If you know equation number 2, can we figure out what is that function? So let's look at like a simple situation first, and then we can see what's going on here. Okay, so the motivation. So let's look at this problem. So let's say let fxy equal to x cube minus xy squared plus y equal 3. Let's say that. And then we can write dz, the differential of this function, dz equals, so what's the differential? Let's take the first partial derivative with respect to x. So it is 3x squared. We're going to consider y is a constant, that's what it means. And then minus, if y is a constant, so y squared is just a constant. So if you take the derivative with respect to x, you get y squared. Okay, this is a partial derivative with respect to x. So you treat y as a constant. So that means wherever you see y, it looks like a constant, times dx plus, now you take the partial derivative with respect to y. So the x is a constant, so the x3 derivative is going to be 0, and then from the other one, if you take the derivative with respect to y, you're going to get negative 2xy plus 1 dy. Now this is a constant function, is equal to 3, so that means the differential is 0. Okay, so what you have here is, so this is the partial derivative with respect to, so we write dabba, not d, dabba, partial derivative with respect to x. That is the partial derivative with respect to y. Good. So now the question is, if you know this, if you know star, can we find the function back? Okay, so you can see that what you did, you didn't do much. You took the partial derivatives and write this star equation. So the question is, okay, so the question is now, knowing star, can we find the function? Can we find the function f? Can we find the function f? So what we try to do, we try to go backward, because you took the partial derivative, now you get the partial integral. Okay, so let's do that. So so if you go backward, what will happen? Because we know that the first part, da by f over da by x equal 3x squared minus y squared. Now what we're going to do, so this you get after taking the partial derivative with respect to x. So now what we do, we integrate this one with respect to the x variable again. So just integrate, thinking that y is a constant. So if you do that, then you should get the function back, because if you integrate this one, you're going to integrate this one with respect to x. Okay, so you're going to integrate with respect to x. So if you do that, you're going to get f x y. If you integrate with respect to x, just create y as a constant. So if you integrate, you're going to get x to the cube minus, so y is a constant, so like you are integrating a constant, so that means you're going to get x and then y squared. But there's a slight new term here, because you took a partial derivative, so we don't know whether there was a constant function of y. So that means if you once you integrate, you need to add that constant function of y. So it's not just a constant, but it's a constant function of y. The reason is, once you take the derivative, if there was such a function, that's going to be 0. That means if you want to go backward, since we don't know whether there was a 1, we just add the 1 in case. Do the same thing. Now if you do the other one, da by f over da by x, da by y, which is equals to negative 2xy plus 1. But now we do integrate with respect to, because you took the partial derivative with respect to y, so you integrate with respect to y to go backward. So integrate in y. So again, you get the same function. So what do you get? If you integrate this one, you're going to see that, so you have to integrate with respect to y. So if you integrate with respect to y, x is a constant, so you're going to get negative x y squared. 1 means if you integrate 1, you're going to get y plus the same argument, because you take the derivative with respect to y. So if there was a function only of x, that's going to be 0, so we don't know. So what we're going to do, we're going to add a function in case. So now, but we know that this has to be the exact same function. It's not a different function, it's the exact same function. So that means it tells you a lot, because since this is the exact same function, you're going to see that this part is common. That means this should appear in the function. But what else? You know that there should be a y function, or this tells you what is that y function. It is y. And also we know that there should be a x function, and we know that what is that x function? That is the x function here. So that means we figure out the x function, the y function from the other one. So that means you can write the answer now. okay, because because it shall be the exact same function, but the thing is that there are some unknown function, but the unknown function you can find from the other one. So that means this suggests that this suggests that fxy equal what we normally do is we can write the common part first, and then the common part once. We can write twice. We write the common part once and the uncommon part once. That means what's the uncommon? x3 is uncommon, and what's the common one? xy squared, and again what's the uncommon one? Y. So that is the function you are talking about. So you can say this equal to a constant. So that means your function that you are looking for is this part, okay. So that's the function you were looking for. So that's equal to c. So don't forget that you always need to equal to c. So that's exactly what's going on here. So you can see it's not that difficult. So what we need to do is we need to make a systematic study. So let's look at the theory behind and how we actually gonna figure out what's going on here. Okay, so I'm going to start with some definitions first. So let's start with what we mean by an exact equation. So the definition: exact equation, exact equation. A first order differential equation, differential equation of the form so we can write m here. So there are some special terms that we use. So we're going to say m is a function of xy dx plus n a function of xy dy. This order matters because we can use this order in the formula. So we start with m and then dx, and there's a plus sign, and then n dy equals 0. So that's the special form. Okay, is exact if there is a function z equal fxy such that if there is a function z equal fxy such that the m xy equal to the partial derivative of x and n xy equal to the partial derivative of y. So that means if you can find a function such that the partial derivative of x of the function is equal to m function and the partial derivative of y is equal to the n function. So if you can find such a function fxy, then we call this differential equation is exact. Good. So and then yeah, so yeah, so that's how we write the differential equation. Remember, there's a plus sign here and the x y, so the order matters. We write x first and then y. We write m and n, so such that the x partial derivative equal to the first part, the y partial derivative equals to the second part. Good. So let's talk about a criteria, how to find such a function. So the theorem, criterion criterion for an exact equation. So criterion for an exact equation. So so let m xy and n xy be continuous, and have continuous first partial derivatives and have continuous first partial derivatives continuous first partial derivatives in a region R, then a necessary and sufficient, condition for m xy dx plus n xy dy equals 0. So you can see that this is a differential equation. Okay? That's a different to be an exact differential equation is to be an exact differential equation is to be an exact differential equation differential equation is, what's going to happen? It is dabba m over dabba y, the other variable, equals to dabba n over dabba x. So that is the condition that it need to satisfy. Remember, it's the other variable. Okay. So the x part you're going to integrate with respect to y. X part you're going to take the derivative with respect to y. N part, that's the y part, you're going to take the derivative with respect to x. Okay. So let's go back. So so what it says, you know that the dx, so that means this is the part related to x, but you can take the derivative with respect to y. And here n is the part related to y, but you take the derivative with respect to y. So it's just the reverse one. Okay, that's what you need to understand. And the interesting part is where this is coming from. So you can see that if you look at the so we can kind of prove that here. So we can write a kind of knot. Yeah, so that's the one we're going to check. So that means if this satisfies, we call the differential equation is a exact differential equation. Remember, it's always the opposite one. So let's write a knot. So by comparing, we know that the dabba f over dabba x is the m function, and dabba f over dabba y is the n function. That's how we normally write it. Now from advanced calculus, from advanced calculus, if m and n have continuous first partial derivatives, have continuous first partial derivatives, then we know that we discussed this in the characterization also. We know that the mixed second derivatives are equal. So that means we know that the da by squared f over da by y da by x is exactly equals to da by squared f over da by x da by y. So the mixed second derivatives are equal. Even if you change the order, they are the same. So that's what we're going to use here. So because of that, so what's going to happen now? Then what is da by m over da by x? Da by m over da by y. So you can see that you can take da by over da by y out. It's not d, it's a da by. And then we can replace m by the definition. What is m? M is da by f over da by x. This is the m function. That's the m function. Plus, now what's going to happen? It's exactly equal to, by the theory, we know that if you switch the order, it's the same. So that means that this is exactly equal to da by over da by x, da by f over da by y. So it's coming from here. Okay, because they are the same. Now we can replace this, because we know that the da by f over da by y means n. So that means this can be da by n over da by x. That's why it's going to switch the order because of this argument. So this is the n function. Okay, that's coming from the definition. So that's the proof. So because of the second partial derivatives, because of the second mixed partial derivatives are equal, you end up getting this relation. Okay, so that means we can use this as the criteria to check whether a differential equation is exact. Good. So let's talk about how the method works. So let's talk about the solution method. So we can say method of solution. Method of solution. The first one, given an equation, m x y dx plus n x y dy equals 0. We can check whether da by m over da by y equals da by n over da by x. So that's the checking part. We can check whether this is the case. Okay, and then what's going to happen? If this is a yes, then it is an exact equation. If this is no, there's nothing we can do, so we can stop because it's not exact. Okay, so because it's not exact. Good. So the second step, now what we do, if it is exact, then we know that according to theory, we know that there is a function f x y which is equal to c. So the goal is to find this function such that we know that there is a function such that da by f over da by x equal m x y and da by f over da by y equal n x y. What we normally do is we pick the easy one to work with, okay, because out of them maybe one is easy. If both are the same, we normally go with the first one. Now let's say we pick the first one. Okay, so what we normally do is, I'm going to write it here, pick the easy one. Pick the easy one. Okay, so we pick the easy one to work with. Pick the easy one to work with. Good. So number 3, now what we're going to do, we're going to integrate. So if you, let's say you start with the first one. If you start with the first one, it is a partial derivative with respect to x. So to reverse the process, you're going to integrate with respect to x. So integrate. So let's say you start with the you pick the first one. So let's say I'm going to pick the first one. It's not a must, but let's continue the process with this. So let's say we pick that. So if you pick that, we can integrate. We can integrate with respect to x. But if you pick the other one, you have to integrate with respect to y. So if you do that, if you pick this one, then what's going to happen? This is simply, if you integrate, you're going to get the function back equal the integral of m x y with respect to x. But remember, this is a partial integral plus, and we know that there may have been a function of y alone, so we're going to leave that function there in case. Number 4. Now what we can do, we need to figure out what is the g function. To figure out that g function, we're going to look at the other part. We know that the y partial derivative has to be equal to the n function. The y partial derivative has to be the n function. So what we do, we're going to take the partial derivative with respect to it. So differentiate with respect to y now, and set it equal to n, and set it equal to n function. Why? Because we know that the y partial derivative is equal to the n function. So let's do that. So what we do, we can take the y partial derivative. So that means you're going to integrate this one with respect to y. So partial derivative of this function m x y dx plus, see, if you take the, because this g function is a function of y only, that means if you take the partial derivative, it's just a regular derivative, so you end up getting g prime y here. Now what we can do, we can set this equal to the n function. We can set this equal to the n function. Now the goal is, we know both of these. You can see that we know this part and we know that part. So that means you can solve for gy. Okay, so that's what we're trying to do next. So this says that g prime y equal n xy minus dabba over dabba y, the integral of over dabba y, the integral of m x y dx. Since you know both functions, you get expression. So now your goal is to solve for gy by integrating with respect to y. By integrating with respect to y. Once you do that, you're going to get the gy function. Okay, so you solve for y. Okay, so you solve for y. Okay, so and then step 5. So then you can write in this case. So but so what's going to happen if you look at the previous step? You can see here. You can see that fxy. So we know this part, and then the gy function. But now we know the gy function. That means we're going to come back and substitute here. We're going to come back and substitute here. So because of that, then what we can do, then f xy equal the integral of m x y dx plus, we already know the gy function, so we know that now. But the theory says that your final answer is not this. This is not the final answer. You have to set this equal to a constant. Okay, so good. And then you can see that this is a, if you then fxy, and this gives, you can say this gives an implicit solution for y. So it's not explicit, it's implicit solution. So what we normally do is we're gonna solve for y if possible. Okay, so and then the last part is solve for y if possible. Yeah, so you can see that, you know, this process has like 6 steps here, a little long. So let's go back and try to understand what they were. So you're going to start with the differential equation. It has to be in this form: m first dx and then plus sign n dy equals 0. What you do, you look at the reverse partial derivatives. You're going to take the partial derivative of m with respect to y, and you see whether that's equal to the partial derivative of n with respect to x. If this is the case, equation is exact. So that means there is a function fxy equals c. So there are 2 parts, the x partial derivative, y partial derivative. You can start with one of them. We normally go with the easy one. You go with the easy one. So let's say you start with x1. If you start with x1, then you integrate with respect to x. Once you integrate, you're gonna get a function. You integrate with respect to x, but plus a g function. Now the goal is to find the g function. What we normally do is we take the partial derivative of this whole equation again with respect to y, the other variable, and then you set that equal to the n function. Once you do that, you can see that only thing that unknown is the g prime y, the derivative of g. And then what we're gonna do with that is we're gonna integrate. We can integrate that. So we have this function. If we say g prime y equal nxy minus the partial derivative of with respect to y, what we can do, we're gonna solve this one for gy. How to do that? By integrating with respect to y. Once you integrate, you're gonna get the function gy, and then you're gonna go back and substitute that into the fxy function, and then your final answer is you set this equal to a constant. Okay, that gonna give you a implicit solution for y. So sometimes what you can do is you can solve for y. Okay, so let's look at this in several examples. So let's start with the first one. Example number 1. Solve, let's say 3 x squared minus y squared dx plus minus 2xy plus 1 dy equals 0. So this is the problem we start with. So let's see how we do this in a systematic way now. So the answer here, the m function is equal to 3x squared minus y squared, and the n function is negative 2xy plus 1. So this is the m function, and that is the n function, and it has a plus sign, so everything looks good. Now we can check the condition. So let's check the condition. So check the partial derivative of this with respect to y. So if you take the derivative with respect to y, what do you get? You're going to get x is a constant, so you get negative 2y. And now let's take the partial derivative of the n function with respect to x. So you can see that you again get negative 2y, so that means this is exactly equal to da by now da by x. So that means yes. So this equal implies that exact equation. So that means this is exact. So this is exact differential equation. In other words, there is a function fxy equal constant that satisfy the two partial derivative condition. So that the goal is to find that function. So we're going to follow the steps. So let's start with the easy one. I mean, in this case both are easy. So now let del by f over del by x equal to the first part. This is a partial derivative with respect to x, so you're going to integrate with respect to x to go back. Integrate with respect to x. So if you do that, you're going to get the function fxy equal to, this is integral with respect to x. So this x cube minus this y is a constant, so x y squared plus the unknown function y. Okay, so I'm going to call this alpha. Now what we do, we define the gy. You take the derivative with respect to the other variable. So differentiate with respect to the y variable. Differentiate with respect to the y variable. So you're going to get del by f over del by y, which is equals to, if you take the derivative with respect to y, you're going to get x is a constant, so you're going to get y means negative 2xy is a y function, so that means just the regular derivative. Now what we do by the theory, you're going to set this equal to the n function. N function is negative 2xy plus 1. So once you do that, you can see something interesting. You can see that this part is exactly equal to that part. In other words, this and that has to be the same. Okay, this should be the case always. So this says that, this implies that g prime y has to be equal to 1. So now what we are going to do, we can integrate this one with respect to y. Okay, so integrate with respect to y. So if you do that, then you're going to get gy. If you integrate, you're going to get just y, and we are not going to add the constant here. We just get the function part, no y. Okay, so we're going to ignore the constant. Okay, ignore the constant. Good. So that means we find the y function. Now we're gonna go back and plug into alpha. Okay, so by alpha we have fxy equal x cube minus xy squared plus gy equal to y. But this is not the answer. You have to set this equal to a constant. Okay, so thus the implicit solution is just get that part, so we can write this one as x3 minus xy squared plus y equal constant. So that is the solution. Okay, that's the implicit solution of y. If possible, you can solve this one for y. In this case, you might have to use the quadratic formula to solve for y, but we can even leave it like that. Okay, so I wanna make something. So I wanna give you some important note here, and you have to write this, the last part, as the final answer. Don't just leave like fxy equal x3 minus xy squared plus y as the solution. That's not the solution. You have to set that's equal to a constant. That's the function you are looking for. Okay, so let's make those notes. Note 1, fxy equal x3 minus xy squared plus y is not the solution, to the differential equation. It's not the solution to the a differential equation. Okay, it is x3 minus xy squared plus y equals c. That's the solution. Okay, so let's write the solution in this form. Okay, you are looking for the constant function. That's that constant function, and if possible we solve. Okay, so we don't know. Okay, so let's write the steps again, and then note 2. So let's say if you pick da by f over da by x equal mxy, picked. If you pick this one, what are the steps? You can integrate with respect to x, differentiate with respect to y, and then integrate with respect to y. So those are the 3 steps if you pick the m function. Now if you pick the other function, if da by f over da by y equal n was picked, now what we can do, we can integrate with respect to y and then differentiate with respect to x and then integrate with respect to x. So you can see it's gonna change the order. That's it. So whatever easy we're gonna pick. Okay, so let's do another example. So we can do like about 3-4 examples. So let's do this one. So example number 2. Solve 2xy dx minus 1 minus x squared dy equals 0. And if you look at this differential equation, you can see that this is not in the right form because there's a minus sign. You cannot do with minus sign, it has to be a plus sign. So that means we can rewrite this one. So the answer, first rewrite as 2xy dx with the plus sign, switch the sign inside. Yeah, because you're going to multiply by extra negative sign, so that means this you can write as x squared minus 1 dy. So that's the first thing to do. You have to bring it to the right form, and once you bring it to the right form, you know everything. And then this is the m part and that is the n part. Good. Now check whether this is exact. You take the partial derivative with respect to y, then you're going to get 2x, and then you take the partial derivative with respect to x, then you're going to get 2x. They are equal, so that means this is exact. Good. So this is exact. This is an exact equation since da by m over da by y equals to 2x, which is exactly equal to da by n over da by x. So that means it is exact. Now we can start with that. We know that da by f over da by x has to be the first part. That's the first part. Integrate with respect to x, integrate with respect to x, then you're going to get da by f xy. If you integrate with this one with respect to x, you're going to get x squared y plus the unknown y function. Now what you do, take the partial derivative with respect to y and set it equal to the n function. So taking partial derivatives with respect to the y variable, you're going to get by f over by y, which is x squared plus g prime y. You set this equal to the n function. What the n function? X squared minus 1. Okay. Now what we can do, you can see that this says that this part has to be equal to that part, because the other parts are equal. So this gives g prime y equal -1, and then we're going to integrate this. If you integrate this one with respect to y, you're going to get gy equal -y. We don't add the plus c. So then you can write your fxy function, because you found the unknown function. This is x squared y minus y. So this is not the solution. What we do, we can set this equal to a constant. That's the function looking for. Okay. So now what we can do is, in this case actually you can solve for y. So we're gonna go ahead and do it. So therefore x squared y minus y equal constant, and you can factor this. So you're going to get x squared minus 1 equal constant, and we can divide both sides. So solving for y, y equal c over x squared minus 1. This is valid when x not equal to plus or minus 1. Okay, so that means you have to remove those two points from the domain. Good. So let's do another example. So example number 3. Solve let's say 3 e to the 2y minus y cosine xy dx plus 2x e to the 2y minus x cosine xy plus 2y dy equal to 0. Yeah, this is like little long one. This problem actually taken from ZIL book. So we're gonna say a note. Good. So what we can do, so you can see that this is an exact equation, and so the answer, this is exact, this is exact, since if you take the partial derivative da by m over da by y, what do you get? If you take the partial derivative with respect to y, you will get 2e to y. If you take the partial derivative with respect to y, you can see that this is a product. So you have to use the product formula. So if you use the product formula, what do you get? X is a constant, so the constant comes out, that means x comes out, but the cosine, that means it's a negative sign, that means you can plus. So it's going to be xy sine xy. And now if you take that's the derivative of the second one. If you take the derivative of the first one, it is simply 1. That means you're going to get negative cosine xy. So this is equals to that's that. But you can see that this is exactly equal to the partial derivative of the n function with respect to x. So you can see that this works. That's the n function, and this is the m function. Good. So those two are equal. That means this is exact. So there is a function. There is a function fxy such that the dou by f over dou by x equals to the first part e to the 2y minus y cosine xy. Now what we do, we can integrate this one with respect to x. So let's do that. Integrate with respect to x. So integrate with respect to the x variable. So you're going to get dou by xy. If you integrate with respect to x, what are you going to get? X e to the 2y minus so what is the integral? If you integrate with respect to x, what will happen here? So you can see that y has been taken out. So that means if you integrate, it's simply going to be negative sine xy. So it is negative sine xy plus the unknown function. Now we're going to differentiate with respect to y. So you get dou by f over dou by y equal to x e to the 2y minus. So take the derivative with respect to y. So that means x comes out and sine become cosine xy plus g prime y. You set this equal to the n function. Once you compare with the n function, you see that g prime y has to be the 2y. It says that gy equal y squared. So then what you can do is because we figure out the y function, we plug in that. So that means this is x e to the 2y minus sine xy, the g function y squared. You set this equal to a constant, and you can see that so this is the implicit solution that we are looking for. Okay, so which is, so you can say this is an implicit solution for y. And the note is in this case it is impossible to solve for y in closed form. Okay, so you can write y equal a function of x. You can do that because you have e, you have sine, you have y, like all of the functions. So so it is going to be difficult. So we can leave it like this. So let's do one last problem and taken from the same book. So let's do that. So this is the last one. So example number 4. Solve the initial value problem. dy over dx equal x y squared minus cosine x sin x divided by y 1 minus x squared along with y0 equal to. So again taken from ZIL book. So I'm going to give you the more information in the description. This is one of the very good book in differential equations. Okay, so let's look at the how we can write a possible answer. So what we can do, you can see that this is not in that special format. So what we want to do, we want to write this using the differentials in that special format that equals 0. So let's do that. So rewriting in the standard form, so what we're going to do, we're going to multiply by dx both sides, and then we're going to multiply by y over 1 minus x squared, and then bring everything to one side, and you can see that you end up getting this. You end up getting cosine x sin x minus x y squared dx plus y 1 minus x squared dy equal 0. So it's easy to see the m function and the n function, those two functions. So let's check the condition, and you can see that this is exact. This is exact since da by m over da by y, if you take with respect to y, what's going to happen, it's going to be negative 2xy, and that is exactly equal to da by n over da by x. So this x. So now what we can do, just pick whatever part you like. So we're gonna just may as a change probably pick the other one now. Okay, so select da by f over da by y equal y 1 minus x squared. Now what we can do, we can integrate this one with respect to y. So integrate with respect to y variable. If you do that, you're going to get fxy. If you integrate this to y variable, what will happen? It is y squared over 2. 1 minus x squared, that's a constant, plus a function of x. We have function of x now. So what do you do? We're going to take the derivative with respect to x, because we need to find the x function. So let's take the derivative with respect to x. So we're going to differentiate with respect to x. So if you do that, you're going to get da by f over da by x equal y squared over 2, that's a constant. If you take the derivative of the inside function, you will get negative 2x. So if you simplify, it is negative x y squared plus h prime x. So you can set this equal to the n function, which is cosine x sin x minus x y squared. That's those two perfectly match. So this implies h prime x is simply equals to cosine x sin x. Now the question is, you can integrate this one. Integrating integrating, you're going to get hx. So you're going to integrate cosine x sine x dx. Actually this is a easy integral, because you can see that what we see here. So if you consider this as the function, you can see that this is the derivative of the function. So that means we can use the power rule. So if you use the power rule, this we discuss in the 4 formulas. That's why I write FF for formula. I got the 4 formula. This is simply 1/2 sine squared x. We don't add the c here. Okay, good. So you find the function. Now what we can do, we're gonna substitute that in the f function. So then you're gonna get fxy, which is equals to y squared over 2 1 minus x squared, plus you find the function. This is 1/2 sine squared x, which is equal to c, a constant. So we can do something interesting now. We don't know the c, so what we can do, we are given some relations between x and y. We can use that to find c. So we can say using using y0 equal to, y0 equal to means when x equal to 0, y equal 2. So we're going to plug in that. So y equal to, so 2 squared over 2, x is equal to 0 plus 1/2 sine 0, sine squared 0. But we know that sine 0 is 0. So this is 0. So this one is equal to c. What this says that? This says that c equal 2. So c equal 2. Since c equal 2, we can plug in that there. So so that means the implicit solution, the implicit solution is y squared over 2 1 minus x squared plus 1/2 sine squared x equal 2. Or you can just multiply by 2 and write this as little comfortable form. So multiply by 2, so you're going to say plus sine squared x equal 4. So that is the implicit solution of y. Actually this one is not that bad. You can actually solve for y, because you can bring this to the other side and solve. So this one you can actually solve. So you're going to get 2 different solutions in this case. So the explicit solution, so you can say then y, so you can bring that to the other side and divide and take the square, then y equal, there are 2 solutions, plus or minus. We can say it is 4 minus sine squared x over 1 minus x squared square root. So that's the solution. There are 2 solutions depending on what part we need. Okay, good. So it doesn't matter, you can even write this as implicit solution or explicit solution depending on whether how easy or how difficult. Okay, so so this is the end of the exact differential equations. Now the question is, so I'm going to give you a question. So the question is, what if the equation, the differential equation m xy dx plus n xy dy equals 0 is not exact. in this case, like, we're going to use a similar approach as we did in first order linear equations. We're going to use a integrating factor method. Okay, so we're going to use integrating factor method. So we can discuss that in a future video. Thank you.